Now I am going to discuss about linear variable displacement transducer, that is nothing but LVDT. So this LVDT works on the principle of mutual inductance. So this works on the principle of mutual inductance, and the displacement, which is a non-electrical energy, is converted into electrical energy. So by using this LVDT, you are measuring the displacement, which is a non-electrical quantity. So that non-electrical quantity is converted to electrical energy, and that is measured. So that is the working principle of linear variable displacement transducer. So the construction diagram of this linear variable LVDT is like this. So this consists of, this is a hollow cylinder. This is a hollow cylinder on which the primary coil is winded at the middle. So this is the primary coil, and the secondary coil consists of two windings, coil 1 and coil 2. So this coil 1 and coil 2 will be having same number of turns. So coil 1, if coil 1 has n number of turns, the coil 2 should also have the same n number of turns. This primary winding is connected to the AC supply. So this can be shown, redrawn like this. This is also the LVDT diagram only. This is the primary winding. So this primary winding is connected to the AC supply here, and other side of this iron core there is two secondary windings. This is the coil 1 and this is secondary coil 2, and the core is placed in between these two coils. So this core will be having an arm here. So by varying this arm, either right side or left side, you can vary the displacement. So by varying the displacement, you can measure the inductance. So by this is the working principle. So and so here these two secondary coils are connected in series of position, so that you can convert these two into one signal. So here the secondary winding EMF, when you supply voltage to the primary winding, then an EMF will be induced in the secondary winding from the core. So if the core is in between these, exactly in between these two, there is the voltages induced in the secondary windings. Consider the voltage induced in the secondary winding 1 is equal to V1, and the voltage induced in the secondary winding 2 is V2. Now the total output voltage is nothing but the difference of these two voltages, that is V1 minus V2 is the total output voltage. So this is about the working principle and the construction diagram. So this will be having a knob here. By using this knob, you can move left side or right side. Okay. So now this can be explained by using this 3D diagram here. So you can observe, this is the hollow cylinder. Inside this hollow cylinder, you are placing this core. This is the core, and these two are the primary windings on either side of, on both sides of the primary winding. So this is one secondary winding and this is the other secondary winding. So and this is the core, which can be moved either left side or right side. So this is how it exactly looks like. Okay, now considering the working position, see here, this is the primary winding for which you are connecting the supply. Both sides of the primary winding you have the secondary windings S1 and S2, and under that you are placing a core here. So consider this core is in the maximum left position. So this side, if it is here, that means more amount of flux is linking with S1. More amount of flux is linking with S1, and there is less amount of flux linking with S2. That means more voltage is induced in S1 and less voltage is induced in S2. That means S1 voltage is greater than S2. Therefore, the output voltage is equal to E1 minus E2. E1 minus E2. Likewise, when the core is exactly opposite to the primary winding, then what happens is there is same flux induced in both the windings, S1 as well as S2. There is same amount of flux induced. So because of that flux in S1 there is E1 voltage induced, and in S2 E2 voltage is induced. Both voltages are same as the flux linking is same. The voltages induced are also same. So that means output voltage E out is equal to E1 minus E2, that is equal to 0 volts. Next, consider the position when the core is at the maximum right. That means core is near to S2. So what happens? The flux is more linking with S2 and less flux is linking with S1. That means less voltage is induced in S1 and more voltage is induced in S2. So therefore, what will be the output voltage now? The output voltage is equal to E2 minus E1 because E2 is greater than E1. So likewise, you can get the output voltage. Okay, and this can be, from all this we can make these conclusions. So what are the conclusions are? The direction of the movement of an object can be identified with the help of differential output voltage of LVDT. That means based on the difference voltage of E1 and E2. That based V0 is equal to E1 minus E2. If the output voltage E0 is positive, what indicates that this means an object is moving towards the left from the null position. That means if E0 is negative, then what happens? The object is moving right position. So here, if the object is moving in this left position, so E1 minus E2 is positive. If it is moving to the right position, then E1 will be very small and E2 will be greater. So E1 minus E2 will be negative. That is the output voltage. So that is the second point here. Similarly, if the output voltage E0 is negative, then this means the object is moving towards the right of the null position. And the amount or magnitude of displacement is proportional to the differential output of LVDT. So the displacement is proportional to E1 minus E2. The more the output voltage, the more will be the displacement of the object. So how much voltage you are getting, so more voltage means more displacement has happened. So if you take the core out from the former, then that means the net differential of the output of the LVDT will be 0. So if you take completely the core out of the former, then what happens is there is no flux linking with the secondary coil, both the secondary coils. So both voltages are 0. So output voltage is also 0. So the differential voltage is 0. So in fact, corresponding to both the cases, whether the core is moving either left or right to the null position, then the output voltage will be increased linearly up to 5 mm from the null position, and after 5 mm output E0 will be non-linear. So that can be explained using this graph here. So initially, for some amount of displacement from 0 to A displacement, the output voltage will be increased linearly. Initially, E1 will be greater than E2, so that the output voltage is positive here. Output voltage is positive, and the displacement is positive. So here till here it is increased linearly, but after that it will not be increased linearly. But if the displacement is in the left direction, then it will be moving this direction linearly, and after that it will remain constant. So this is about the output graph of the LVDT. Coming to the advantages of LVDT, so it is having smooth and wide range of operations. So wide range of displacement can be measured by using this LVDT, and it is having high sensitivity. That means for a small amount of distance also can be measured by using this LVDT, and it is having low hysteresis loss and low friction losses, and it has a rugged construction because it is circular. It is of having rugged construction, so that it is easy to handle, and it requires less amount of power, so low power consumption. Next, direct conversion to electrical signal, so that displacement is directly converted to electrical signal output voltage. and it is having fast dynamic response. Output is having fast dynamic response. Coming to the disadvantages of LVDT, since LVDT is inductive transducer, it is sensitive to stray magnetic field. Hence, an extra setup is required to protect it from stray magnetic fields. And also, it is an electromagnetic device, so it will be affected by vibrations and temperature variations. So, in order to avoid this, you need to consider magnetic field, protect it from the magnetic field, and also you need to protect from the vibrations. So shielding should be provided here. And applications of LVDT are, first application is LVDT is used to measure the physical quantities such as force, either force or tension or pressure or weight can be measured here. And these quantities are first converted into displacement by the use of primary transducers. So by using any transducer, you need to first convert into from force or tension or pressure or weight. First you need to convert all these types of physical quantities into displacement only. So after converting into displacement, you can convert into electrical voltage signal by using the LVDT. Okay, so and it is mostly used in industries as well as servo mechanism, and it is also used in industrial automation, aircraft, turbines, satellites, hydraulics, etc. These are the applications of LVDT, linear variable differential transducer. So in this, the working principle is you will be measuring the displacement by varying the displacement. You can get the output voltage. That output voltage can be measured. So that means the displacement can be measured by using this LVDT. That is the working principle. Next topic is strain gauge. Strain gauge and its principle of operation. So strain gauge is used to measure the strain. So this is the strain gauge. So the construction of this strain gauge will be having. So here you can consider this is the gauge resistance wires. These gauge resistance wires are fixed to this support, so that whenever if you are providing any strain on this wires, what happens is uh, there is some strain produced. That strain, if you measure that strain, you can measure the resistance of this wire, so that you can measure the strain. So we know that the resistance can be measured by using the simple Wheatstone bridge. So this is the Wheatstone bridge. So Wheatstone bridge consists of four resistances, in which one resistance is the unknown resistance, which you need to find out, and the three resistors are standard resistors for which you can know the value. So simply you can consider R1 by R3 is equal to R2 by unknown resistance. From that unknown resistance you can measure. So if the bridge is whenever the bridge is balanced, it means that these values are equal. So when there is no strain applied. When the bridge is unbalanced, there is a voltage reading in this voltmeter. That means that from that voltage you can measure the how much strain is applied. So here, so this is the strain gauge. So if you apply the tension in this direction, that means if you make tension, that means if you stretch this one, that means there is a tension caused. So this tension causes resistances increase. Resistances increase because R is equal to rho L by A. That means L is increased, so that resistance is also increased. And if you compress these two, so if you compress these two endings, then what happens is the resistance will be decreased. And lateral direction, if you apply any force, there is no effect on this strain gauge. Only the on this in these directions only the resistance can be increased or decreased. So this is a, and between these two terminals you can measure the resistance. So these two terminals can be connected in any type of bridge available. Simply we can use Wheatstone bridge. So this is a bonded strain gauge. So this is how you can measure the strain by finding out the resistance. So for that you need from this gauge strain gauge you can derive the gauge factor also. So this gauge factor is defined as the ratio of per unit change in resistance to per unit change in length. So per unit change in resistance to per unit change in length you can measure this gauge factor. So consider this is the wire which is having the length L. So when and this is having a resistance R. When you apply force in this direction, that means when you stretch this one, if you apply force in this direction, what happens is this will elongate here till here. While elongating, what happens is the diameter will be decreased. Even though length is increased, the diameter will be decreased. So this resistance is also increased. So the resistance has been increased from R plus delta R, and L has been decreased from L plus delta L. The gauge factor is denoted as GF is equal to delta R by R divided by delta L by L. So that implies delta R by R is equal to GF into delta L by L. So this delta L by L is nothing but the strain. This is nothing but the strain, and this can be denoted as delta R by R is equal to delta L by L plus 2 mu into delta L by L plus delta rho by rho. So by using this derivation, we can calculate the gauge factor. So gauge factor is equal to 1 plus 2 rho plus 2 mu plus delta rho by epsilon. So here the term 1, that means resistance causes due to change of length. Due to change of length. And 2 mu means resistance change due to change in area. That is Poisson's ratio. This is the Poisson's ratio mu, and delta rho by rho epsilon is equal to resistance change due to piezoresistive effect. So this is about the strain gauge.